in the last lecture we discussed about the front end engineering design concept, where we introduced that some preliminary dimensions or member sizing or layout of the form is required to ascertain that the chosen form is stable and the chosen form is strong enough. So, there are many international codes which will govern you to check all these aspects which we saw in the last lecture. So, essentially before we do a detailed dynamic analysis, one must do basically in place analysis using a software. We will quickly see how and what are the steps involved in picking up any one software of this nature and see how can you model it in for a fixed type structure in this lecture. So, let us take up the software SACS, which is useful for doing in place analysis of jacket structures. So, you have to first define the basic jacket framing, which will talk about the layout in terms of its elevation and plan for the member sizing available, and this can be done using the jacket wizard in Precede Pro in the menu, which defines the leg batter. Batter is nothing but the slope of the leg, because in jackets you will see that the leg is not vertical. The leg is not vertical. If this is your top hull, the leg is not vertical, the leg is inclined, and we call this as actually a batter, nothing but the slope. So, what should be the slope of the, this is the initial line, that is your original leg. So, you have to specify the batter, then the spacing, and of course of the legs and the skirt pile details if you have anything of that nature. Then title this input file as SAC input dot star, maybe the extension is generated automatically. Then the file contains basically the model data for your problem, the member characteristics and properties defined using the sections and groups. You have got to, you can even group them, you can give them separate sections for each leg as well. It also contains all the load data, the wind areas, the CDCM values and the marine load details all along the length of the member. Then you have to create the joint can check input file called jcninp.star, where the load cases for which the joint can unity check will be performed is specified in the specific file by name jcninput.star. Then select linear static with PSI analysis option in the run file wizard of the software. The output file PSI list or PSI LST specifies the pile capacities mobilized versus the capacity required and gives a check for unity check ratio, what we call UC. So, it will check the pile capacity ratio and the available capacity which has been imposed on the pile, and we will check whether it is exceeding 1 or lower than 1. So, once open the PSV DB folder, which is the name of the folder automatically generated, and then check the member or the members for the unit check ratios graphically, because graphically it will show whether the member has exceeded the unit check ratio exactly. Unit check is nothing but if you are having a combined action of axial force and bending. For example, let us say I have a cylindrical member which is subjected to an axial force and of course a bending as well, then stress bending by stress bending permissible in x axis raised to the power alpha plus stress bending by stress bending permissible in y axis raised to the power of alpha should be less than or equal to 1, what we call as an unity check. So, if it is a biaxial bending scheme, if it is an axial plus bending, again this kind of similar check of combined ratio of UC will be checked graphically in the file. Then the joint can UC ratios need to be checked in the PS list file which you have created in the previous step. So, once you do this, then the jacket modeling can be done for in place analysis using this particular pull down menu which is called Precede. Precede is a pull down menu. So, click the modeling Precede as you see in the screen here, create a new model, then say OK, then select alphanumeric jacket joint names, for example A1, A3, the joint names are going to be generated, select them with tags, then press OK, assign all elevations, jacket leg battering, spacing, conductor details and skirt pile details now in this model. The legs will appear now and assign the braces members as follows. Select the member, add, select relevant joint and give group label to them and apply. So, keep on adding the bracing members to your jacket. Specify member properties of each one of the added braces now by selecting property and member group. You can always group them in a single one. So, give property to any one member, it will be assigned to all the members automatically. This is how the model will be generated in SACS after you give the details for the bracing. So, the cyan colors what you see here, these are all the bracings which has been generated, these are all the bracings, these are the legs which are having batten and of course different elevations of minus 10, 7, sorry plus 10, 7, 10, minus 20, 30 and minus 50 have been generated for a plan size of 10 meter by 10 meter. So, you can generate a graphical model like this. Then specify the global parameters like marine growth, CDCM values etc. using the C state toolbar available in the software. Then assign loading and load combinations. Perform linear static analysis, very important. We are not doing a dynamic analysis here. So, the example structure what you see here on the right is what you will see on the screen once you follow all the above steps to do the linear static analysis. Subsequently, two different analyses need to be carried out or performed for this kind of structures. One is without marine growth and one is with the marine growth. The load data what you generally use or what has been used in this specific example is a wave height of 8 meter, wave period of 12 seconds and of course, you should check it for different approach angles. We start up with 0 degree here. So, this is how you will see both the figures generated with and without marine growth. The left one what you see is a without marine growth and the right one what you see is a with marine growth file data has been checked and the unit check ratio for the wave loading has been carried out and all the numbers what you see here is giving me the values of unit check ratio. For example, let us take this member is giving 0.68, this member is giving 0.06, this member is giving. So, all unity checks have been approved so that it does not exceed 1. So, this will give you a graphical information about whether any specific member has failed the unity check or not for a given loading condition what you have assumed. If it fails, you have got to change the section group or the dimensions or the characteristics of the member or the entire group once again, redo the analysis, run the analysis once again and see whether unit check has been approved. So, unit check is where we are saying that the structure has become stable to understand the configuration and the members are strong enough to withstand the bending or axial stresses applied on the member. So, once you do this, I have a classical equation of motion here which we already know for a multi-degree freedom system which I will intend to solve. Once we come to this stage, then we will talk about f of t here. So, we already know the force on the cylinder is essentially given by an empirical relationship proposed by, or I should say postulated by, Morrison in the year 1950. So, the reference is So, the researchers Morrison et al. Proposed in 1950 an empirical relationship based on which the force on cylinders can be computed, which is f of t, which we are talking about on the right hand side of this equation. There are some idealizations on this particular f of t which we want to describe here before we do a detailed dynamic analysis for this by solving some examples. So, this f of t, which is a function of z and t, where z is along the height of the member, is a combination of inertia, which is a multiplier of acceleration, plus drag, which is a multiplier of velocity, and so on, where Vx stands for v dot x is acceleration of the water particle. Which in short we can say inertia force plus drag force. The inertia force has got two components again further here, has two components, one from the hydrodynamic, one from the pressure gradient within the fluid. So, which I can separate as Ci is now Cm plus Ca where this is Cm plus rho A where this can be simplified as Ci pi d square by 4. Okay, let us use capital D here. Where d is the outer diameter of the member and Ci is the inertia coefficient of the section. Hence, the inertia force per unit length of the member can be given by Ci inertia force alone, which is C m plus Ca and so on. Which can be further expanded with this, which can be Cm pi d square by 4 of Vx plus rho A Vx dot. We look at the drag coefficient, there is a problem here. The drag coefficient or the drag force depends on the Reynolds number. What we can say simply is half rho CD dia. Now, if you look at the force vector completely here, I am talking about linearization of drag. Why it is required? Because I need to solve the problem, I can linearize it. How it is done is what we will see now. Where it is nonlinear, there is a term here in the original equation where we wrote Vx and Vx getting multiplied with an absolute sign. So, prevent the nature of the force acting on the member. So, let us say for example, if a linearized drag coefficient exists, if it exists, then the force vector now can be given as Cm Vx dot plus Cd bar Vx plus Ca Vx, this acceleration, plus Cd of Vx absolute Vx minus Cd bar Vx. It is the same equation which I wrote earlier. I have now added and subtracted a new term, these two. So, from these two I will pick up the error function. So, I can rewrite this equation as f can be now rewritten as Tm Vx dot plus Cd bar Vx plus Ca Vx dot plus E, where E is the error function. Now, I can minimize this using least square approximation. Using least square approximation, I can minimize this error function as below. So, the second derivative of this error function with respect to the Cd bar is simply given by minus 2 of where the symbol is the time average. And that to be set to 0. I am minimizing it. So, there is a Cd here, there is a Cd here, I will rewrite it again, minus 2 Cd, there is a Cd here anyway, Cd here. So, I am doing a least square approximation. So, Cd square Vx Vx minus Vx square within a time average set to 0. So, from this equation I can easily find Cd bar as this is going to be Cd bar, right, Vx is Cd bar. So, from this Cd bar can be which I want, it is a linearized Dirac coefficient which is Cd times of, because I am setting it to 0, Vx square absolute Vx by Vx square, of course a time average of this, and of course a time average of this. Now, for a Gaussian non-zero mean process, we can simply say Vx square absolute will give me the sigma Vx square, that is the variance, and Vx alone, the time invariant, will give me, this is sigma Vx. approximately root 8 by pi of sigma Vx, if it is a Gaussian process, and the numerator time variant of Vx square Vx will now be root 8 by pi sigma Vx cube. So, substitute back in this equation, I get C d bar as C d times of C d, the C d is already here, Vx square cube and Vx square. So, I will get root 8 by pi sigma Vx. That is my linearized drag coefficient. So, I can use this instead of having a nonlinear drag term in my f of t. But the only difficulty in this equation is I must know the statistical distribution of the velocity of the water particle. And hence now, knowing the statistical distribution, that is sigma Vx of the water particle velocity I can now say my f of z of t is simply Ci Vx dot, that is acceleration, which is an inertia coefficient, plus C d root 8 by pi Vx sigma Vx. I just replace the linear term, the square term, with this equivalency of 8 by pi. I will call this equation number 2. Now, the question is, in an offshore structure, what we just now saw an example, I have members which are vertical. So, members can be aligned in many ways. One, it can be vertical, that is parallel to z axis. It can be horizontal, parallel to x or y axis. The most importantly can be inclined. If it is inclined, how do I do my force? So, f of t for an inclined member. So, first step what we generally do in such analysis is we can linearize the drag term by this approximation, which is given by, so force on inclined member So, the general expression of Morrison equation in vectorial form is given by let us say n, we are talking about an arbitrary orientation plus C d of V. It is a general equation without linearizing it. Let me call this as equation number 3. Now, I have a member, okay, in this case V n and V dot n are normal velocity and acceleration, and the bar stands for, let us say, the vector modulus. Now, I have a cylinder or I have a member which is arbitrarily oriented like this. C be the component along the member, and the angle with which this member axis makes with Z is alpha. And let this be beta. So, for a vertical cylinder, Vn can be replaced as Vx, because the force is normal. We are talking about Vn is nothing but the normal velocity or acceleration. With the cylinder is vertical, I can always use Vn as Vx in my calculation, where x is in the direction of propagation of wave. So, we will use this equation again, number 3, and try to expand this vectorially. So, now C is the unit vector along the axis of the inclined member. Of course, as shown in the figure. Now, this has got to be resolved parallel to the member and normal to the member axis. When I try to do that, I call these two components as Vt and Vn. Respectively, tangential and normal components respectively. That is, Vt is the component parallel to C vector and Vn is the component normal to C vector. So, therefore, I can write Vt as V of C and Vn as, or we will say V is Vt plus Vn. Therefore, now I have Vn as, I will remove this, that is V minus Vc of C. Now, when the wave is travelling only in the positive x axis, the y component of this wave will be 0. Hence, I will draw the figure once again here. This is my x, my y, z, this is my member which is C, this is alpha and this is beta. So, the projectile of this on this plane will be 0. So, there are two planes normal to this. Z y plane has got two planes normal, one is x y, other is z x. This will be 0 because the y component is 0 here. Therefore, I will get back to this plane. I can write simply Vn x, I am looking here, Vn x as Vx looking here minus of Vx Cx plus Vz Cz of Cx. Similarly, if you want to do the normal component Vn x in terms of y, I should say Vy minus Vx Cx plus Vz Cz of Cy, but we already know Vy is 0. Similarly, Vnz is Vz minus Vx Cx plus Vz Cz of Cz. You can see all these products are happening only on the xz plane. Now, these multiplies what you see here, okay, I will remove this figure, there is a small confusion here, I will just erase this and write this as x. Okay. The direction cosines what you see here can be expanded as the corresponding projections of this vector on the respective plane. Therefore, I can say Cx, Cy and Cz are given by the direction cosines are sin alpha cos beta, sin alpha sin beta, and Cz in my argument is cos alpha. That is what I am having here. So, it is very interesting for any member which is arbitrarily oriented, whose angle of inclination is known to me with respect to the z axis as well as the projectile on the xy plane, can easily find the force vectors for this member using the same algorithm. I will now substitute these values on my respective Morrison equation, get the force on this member for unit length of the member. So, f of t can be linearized, the drag nonlinearity can be taken away by an approximation as we just now show. Similarly, any member which is arbitrarily oriented other than vertical or horizontal can be also handled in the same fashion. So, the confusion for unit length of the member for the wave force, which is the right hand side equation of motion of this, is can be sorted out by this. Of course, for the left hand side of the equation of this motion, we already know m and k. We will talk about c slightly later when we talk about the next model, because c can be always approximated based upon the first values of m and k, where there are different models advised by researchers to identify the proportionate the damping matrix. So, in my argument, depending upon the added mass value, that is depending upon the submerged volume of every member, I can always estimate the mass matrix and k matrix. K matrix depends upon strength in my equation of motion. We have discussed f of t on different members, which is vertical, which is horizontal, and which is inclined per unit length of the member. And of course, k depends on the geometric sizing, length, material, and boundary conditions or support conditions of the member. I can estimate k, and of course, m depends on the mass, which is lumped as per your choice, and of course, ma depends on the submerged volume of the member or members in a system. So, my whole equation of motion is now known. I can solve this equation of motion to get my response value, which are x of t's, what I will be getting from the solution of this. Any questions here? So, I can handle vertical members, horizontal members, inclined members. I can also linearize the drag term, which is one of the nonlinearity present in the system because of the multiplication component of the velocity vector with the force in Morrison equation. So, if the Morrison equation is not applicable, for example, the diameter of the members are very large, they are not slender, we have to account for the diffraction equations, which I will discuss in the next lecture, how I will handle large volume or large diameter members using diffraction theory, which is again approximation given by different researchers, which we will discuss in the next lecture. Then we will take up an example and solve and show how f of t can be computed in simple terms for both of these models using either linearized drag or using diffraction problems. So, now I have a closed form answer for me that I will be able to estimate my right hand side of this equation of motion. Left hand side is of course a problem formulation for me, which I already know. I can solve this using different algorithms available to me, which I will show you or discuss you in the successive lectures. So, I can solve this in time domain or frequency domain, get my x of t either in time history variant or frequency variant. Okay. So, preluding the dynamic analysis, we require to do a static analysis, which will tell me whether the form assumed by you is stable and strong. So, SACS can be an interesting software which can do this, which can be applied as we showed here. You have got to practice this for making the model and do it. Now, the argument comes here as I explained you in the previous lecture, that if an earthquake force also acts on a given system, how do I model this? How do we account for the earthquake or the ground acceleration onto the system? There are two cases here. As far as fixed jacket structures are concerned, these structures rest on the seabed, resting on piles, etc. So, the direct force of ground acceleration can be implied on this. How to handle this? If they are floating, if they are anchored to the seabed by teethers or some other systems, then how are they transferred? Both cases we will handle. So, in the next lecture we will talk about how to handle in f of t the ground acceleration to which the system is subjected to, and also we will take an example of diffraction problems and see how we can find out f of t for them as an empirical relationship, which is again approximated given by different researchers, because diffraction theory is again more complicated in its numerical algorithm compared to linear velocity potential, as we just now saw in Morrison equation. But not necessarily every problem has a suitability of Morrison equation getting applied. there can be large diameter members as in case of gravity based structures. Okay. So, how to handle them, we will discuss that. So, once it is understood, I should now tell you an algorithm how to solve the equation of motion in a time domain or frequency domain. If I know that, I think I can pick up any problem of a different form, model that, check for stability and strength, get feed approval, then go back to dynamic analysis, find out the member force in each unit length of the member for any orientation of the member, form the problem, iterate it, or write an algorithm to solve the problem in time domain or frequency domain, get the response history in frequency domain or time domain respectively. So, my problem will be completed. Now, the catch lies in different problems or different forms. How do I form actually the problem? How do I get my K matrix? How do I get my C matrix, as I just now said? How to get my mass matrix? So, if I understand this, and very well if I understand how to lump these masses at different locations where x of t is being measured in terms of multi degree as a rigid body motion, which we normally approximate or idealize in ocean structures, I must concentrate to get f of t at those points and do the solution for this equation of motion. Sometimes there is a possibility that this equation of motion can be decoupled, in some cases it is not possible, depends upon whether can you really normalize this mode shape. Okay. So, this is where we are going to take away in couple of lectures from down the line as far as dynamic analysis of offshore structures are concerned in this module. Okay. So, next class will be focusing on how to get the f of t if there is a ground excitation, because now we spoke only about the horizontal loading or lateral loading comes from the waves. Of course, we gave you an introduction how to get this force on because of wind in the first module. This talks about wave because Morrison equation deals only with the wave. Of course, the Morrison equation can be modified when there is a current velocity also. Okay. So, we can use wave and current, we can handle here, but aerodynamic force on superstructure of the hull can be handled separately with a different methodology, as we discussed very briefly in the last module. Okay. So, we are talking about the aerodynamic analysis of the platform. When we talk about aerodynamic, I will tell you how this has been arrived at. So, we will do couple of examples to understand this and give you inferences on this. Any questions here?